Okay, so what are we trying to do? Well, we're still trying to figure out how our model parameters are related to things that we would measure in experiment. So how are M and G related to mFIS and GFIS? Now, it turns out there's a very interesting quantity to study to answer this question. And we're going to study the two-point correlator. So we can learn a lot from the two-point correlator. Good. So what do I mean by this? Well, you know what I mean. I'm taking the vacuum expectation value of the time-ordered product of two fields, phi of x and phi of y. Now, there's two terms, remember. If Tx is greater than Ty, that means that Tx is the latest field, okay, the oldest field. And remember our rule for time ordering, that latest goes leftist. So we'll have a term that looks like that. And then we'll have a second term, which is Ty minus Tx naught. And now the order of the fields is swapped. Good. So that's the usual time-ordered, two-point time-ordered correlation function. Now, this is not what we're going to study. We will study naught, phi of x, phi of y, naught. So regardless of what the values of the times are, we don't swap the two fields around. We're just studying this object. Now, of course, if you've studied this and understood it, it's very easy to reconstruct the time-ordered two-point correlator. And it turns out that there's a lot of good reasons to study this correlator. As we will see, it's very easy from this correlator to, for example, derive a relation between the model parameters and the physical mass. This correlation function has a name. It's called a Wightman function, or Wightman correlation function. Wightman function. Now, Wightman is the name of a person, Arthur Wightman. He was a professor at Princeton, and he developed a lot of rigorous results about quantum field theory. So this correlation function carries his name. Okay, now I want to write down the identity inside Fock space. So what is the identity operator? Well, I need the identity operator inside the state with no particles. I need the identity operator inside the state with one particle. So I integrate over all of the one particle states. I've chosen to work with states that have a definite energy and momentum. You can also see from my measure that I'm working with states that are relativistically normalized, but this is not everything. I now also need to include all of the states with more than one particle. And for these, I'll put an N here to indicate the number of particles. And there is both a discrete sum over the number of particles. So we need to sum over all numbers of particles more than one. And there's also an integral, which tells me to integrate over the momentum of that n particle state. So the way that this identity inside Fock space is working, the first term is the identity inside the subspace with no particles. The second term is the identity in the subspace with one particle. And the third term sitting here is the identity in the subspace with more than one particle. Now, I haven't spelled out that third term in too much detail, and that's because we're not going to need it too much in what follows. Now, let's take this identity and let's insert it into our Wightman correlator. So our Wightman correlator is this. And I now want to insert the identity in between phi of x and phi of y. So I'll get three terms corresponding to the three terms in the identity. First, the identity inside the vacuum sector, the no particle sector. So that's what it is. Then there's a term which will be inside the one particle sector. Good. Actually, I'm going to rewrite this a little. You see, I can take this integral out front. There's no problem with doing that. So let me just do that. Save myself one step. Okay, good. And then we'll have P, 5y, and naught. And then we've got the third term, which is all particle subspaces that have more than one particle. Okay. Good. Now let's treat each of these three terms in order. So let's just have a little aside here. So first of all, we're looking at this expectation value where we've got naught, phi of x naught. If you were dealing with the free theory, you would tell me, well, phi of x acting on naught is a one particle state, and you tell me a one particle state is orthogonal to the vacuum, so you would have predicted that that vanishes. And in the free theory, that does indeed vanish. However, here we're in the interacting theory, so phi of x acting on naught need not produce a one particle state. In fact, it won't produce a one particle state if there are interactions. There'll be one particle pieces, two particle pieces, three particle pieces, and so on. Well, there are situations where there's also a piece proportional to the vacuum. And in those cases, you do have, so I'm saying it can happen, that the vacuum expectation value of the field does not vanish. There's some language that goes along with this. We say that the field phi of x has condensed. So when people tell you that a field has condensed, they can say it more simply by just saying to you, the field has developed a vacuum expectation value. One place where this happens is with the Higgs mechanism. The Higgs field condenses, and the expectation value of the Higgs fields sets the masses for other particles in the standard model. Well, in this case, what we can do, we can define a new field, phi prime of x, which is equal to phi of x minus the expectation value of phi of x, vacuum expectation value of phi of x. In most situations, this term will be a constant. It can happen that it's not a constant, but it will be a constant whenever translation invariance is a good symmetry, is preserved. So there are cases where we talk about the spontaneous breaking of translational invariance, and in that case, this extra term can even depend on x. But the point is, and let me not labor it too much, we can always arrange things so that the vacuum expectation value of our scalar field is equal to 0, okay? So this is always possible to arrange this. We may have to shift the field, but it's always possible. We will assume that we've done this shift, okay? And if we've done that shift, the first term vanishes. Good. So this little discussion here was just to motivate to you that under extremely general conditions, we can imagine that our field has a vanishing expectation value, vacuum expectation value, and that is what I'm going to assume from now on. Good. Okay, so the first term is 0, then plus. What's the second term? Well, this is a matrix element between the field, a one particle state, and the vacuum. So let's take a look. Well, we've studied that over here. We studied k1 phi of x naught, that was z to the 1/2 e to the I k1 dot x. So I am looking at this formula over here, and we're going to be using that formula there. So let's use it now. So what is this going to be equal to? Well, we'll have an integral d3p over 2 pi cubed to omega p From the first matrix element, we'll get a z to the 1/2. From the second, we'll get a z to the 1/2. So we're going to land up getting a z. And then what matrix element did we study? We studied 0, phi of x, kn, and that gave an e to the I kn dot x. So from this 0, phi of y, pn, p, we'll get an e to the I p dot y. Let me just make sure I didn't screw up the sign. Yes, I didn't. Okay. For the other matrix element, the one involving phi of x, you need to take a dagger to swap the position of the p and the naught. And that means that this exponential will be complex conjugated. So I just get a minus x. So my last comment was just saying the equation that you need is obtained by taking a dagger of that box with the green arrow. Okay? So dagger that box and you'll get the equation that I just used. Good. So now I've simplified the second term, and now let's simplify the third term. So this runs over all of the subspaces with more than one particle. And now we simply use the box above the box that we've just been using with the green arrow. So just kn phi of x naught is equal to e to the I kn dot x and this matrix element. So what do we get? Well, we would have e to the I pn dot x minus y, and then we would have the magnitude of this matrix element by naught and naught. Because you see, look at the box. This allows us to relate the field phi of x at position x to the field phi at position naught. So that's what I've done there. And just to stress again, this is an incredibly general argument. All that we've used so far is translational invariance and Lorentz invariance. All that we've used so far is Poincare invariance. Now we're going to need to make use of a function. So let me introduce it. Introduce. And pay attention to this function because it's going to play a little bit of a role. So let's call it delta plus x minus y, comma, mp squared, so that's the physical mass squared, and this is equal to an integral d3p over 2 pi cubed. There is a 2 omega p, and then there is an e to the minus I p dot x minus 1. Good. Okay, we'll continue in a moment.